Hello and welcome to the 6th MCQ video on analog electronics. In this video, I'll be mainly focusing on the Q point or the operating point, then DC load line characteristics of transistors, mainly in the common emitter configuration, that is common emitter amplifier configuration. The major advantage of a phototransistor over a photodiode is its response to higher frequencies, AC operation, increased sensitivity, durability. And here you go. And the answer is increased sensitivity. Most phototransistors have outer casing which is either transparent or has a cleaner lens to focus the light onto the base junction for increased sensitivity. And also in a phototransistor the current gain is too high, and this is nothing but the sensitivity of a phototransistor. But this is not available in a photodiode. That is why the sensitivity of the phototransistor is greater than that of a photodiode. When testing an NPN transistor using an ohm meter, the collector emitter resistance will be low when the collector is positive with respect to emitter, the emitter is positive with respect to collector, the transistor is normal, the transistor is defective. And here you go. And the answer is the transistor is defective. Then the collector emitter resistance will be low. The collector emitter resistance is nothing but the output impedance in common emitter configuration, and typically for an NPN transistor the output impedance is very high. So when testing an NPN transistor, if it shows a low output impedance value, then it means that the transistor is faulty or defective. If the emitter resistance decreases, the Q point moves up, collector current decreases, Q point stays where it is, current gain increases. And here you go. And the answer is Q point moves up. Here the Q point means the output Q point. Q point means the operating point. So the output operating point will move up. So as you all know, we have one input side and the output side. So from the input characteristics and the load line will be obtaining the input Q point, and for a common emitter configuration, I will be discussing mainly common emitter configuration. The base current value IBB can be obtained from that input side Q point value, and then again you will be plotting the output characteristics and the load line, and we will be fixing the base current IB based on the input Q point value IBB. And now if the emitter resistance decreases, what happens is that the flow of collector current is more because the current chooses the low resistance path, and the current gain also increases, and which means the Q point moves up from the previous value. Okay, so that is happening. If the emitter resistance increases, the collector voltage decreases, stays the same, increases, breaks down the transistor. And here you go. And the answer is increases. If the emitter resistance increases, then the more supply of voltage is going to the output load because the current chooses a low resistance path to flow, and so it does not flow through the emitter resistance. Hence the collector voltage will increase. When the current gain increases from 50 to 250 in an emitter biased circuit, the collector current remains almost the same, decreases by a factor of 5, increases by a factor of 5 is 0. And here you go. And the answer is remains almost the same. In an emitter bias circuit, there is no relation between the collector current and the current gain. Hence, it will remain the same. If the collector resistor of an NPN transistor is open, the collector voltage is low, high, unchanged, unknown. And here you go. And the answer is low, because if the collector resistance or resistor is open, then there is no way for flow of the load current, hence the output voltage is low at the load side. If the emitter resistor of an NPN transistor is open, the collector voltage is low, high, unchanged, unknown. And here you go. And the answer is high, because if the emitter resistor is open, then the full supply voltage is appearing across the output load, because the current chooses a low resistance path to flow, so it will not flow through the emitter resistance, hence the collector voltage will be very high. If the current gain is unknown in an emitter bias circuit, dash cannot be calculated. Emitter voltage, emitter current, collector current, base current, and here you go. And the answer is the base current. In an emitter bias circuit, the emitter current IE is equal to current gain times the base current. So if we don't know the current gain in an emitter bias circuit, we will not be able to find out the base current value. When there is no base current in a transistor switch, the output voltage from the transistor is low, high, unchanged, unknown. And here you go. And the answer is high, because in a transistor, if the base current is 0, that is in common emitter configuration, the collector current is also 0. And in a transistor, we know that IC is equal to VCC minus VCE divided by RL. Therefore, we can see that VCC will be equal to VCE, which means the output from the transistor is high. If a transistor operates at the middle of the load line, a decrease in the base resistance will move the Q point down, up, nowhere, off the load line. And here you go. And the answer is up, because as the base resistance decreases, the base current increases, and according to the so we know that the base current is directly proportional to the output collector current. The small change in the base current gives big increment in the output current. And also you can see from the diagram that as the base current increases, the Q point will shift up. If a transistor operates at the middle of the load line, a decrease in the current gain will move the Q point down, up, nowhere, off the load line. And here you go. And the answer is down. Reduction in the current gain leads to reduction in the output current, because both are proportional to each other. Obviously, the Q point gets down if the output current comes down. Okay, so as you can see from the diagram, the Q point will shift down. If the base supply voltage increases, the Q point moves down, up, nowhere, off the load line. And here you go. And the answer is up. The base current increases due to increase in the base voltage, and the small change in the base current gives the big increment in the output collector current, and it means that the Q point will move up from the previous value as the base current is increasing. Suppose the base resistor is open, the Q point will be in the middle of the load line, at the upper end of the load line, at the lower end of the load line, off the load line. And here you. And the answer is at the lower end of the load line, because if the base resistance is open, then there is no path to flow of the electrons or the flow of current from the source to the base of the transistor. Hence the base current is 0, and it leads to the output current very much lower, but there can be smaller leakage currents due to the collector diode. So the Q point goes lower end of the load line, because the base current is 0, so it will come down. If the base resistor has 0 resistance, the transistor will probably be saturated, in cutoff, destroyed, none of the above. And here you go. And the answer is will be destroyed. If the base resistance is 0, then the base current is very high, since we know that the base current is directly proportional to the collector current with the amplifying factor in common emitter configuration. So the value of the collector current is enormously getting high, and in this time the transistor operates in the saturation region and finally it gets destroyed. If the collector resistor opens in a base bias circuit, the load line will become horizontal, vertical, useless, flat. And the answer is horizontal. When the collector resistor opens, the collector current is 0 and we will obtain VCC equal to VCE. Here the load line permanently reaches the horizontal line below the characteristic graph of the transistor. That means the transistor is in cutoff region. The collector current in an NPN transistor is 1.5 milliamps. If the current gain is 50, the base current is 3 microamps, 30 microamps, 150 microamp, 3 milliampere. And here you go. And the answer is 30 microampere. Then again, if there is nothing mentioned about the configuration, we will assume it as common emitter configuration, and we know that beta equal to IC by IB in a common emitter configuration. So we will obtain the base current as 30 microamps. When the Q point moves along the load line, VCE decreases when the collector current decreases, stays the same, increases, none of the above. And here you go. The answer is increases. When the Q point moves along the load line, VCE decreases when the collector current increases. You can see it from the diagram. The base emitter voltage of an ideal transistor is 0 volt, 0.3 volt, 0.7 volt, 1 volt. Here you go. And the answer is 0 volt. Ideally, a saturated transistor acts as a closed switch contact between the collector and the emitter. Hence, there is no need of base emitter voltage to enable the transistor to work in the active region. So it is 0 in the case of an ideal transistor. In the active region of an NPN transistor, the collector current is not changed significantly by change in base supply voltage, base current, current gain, collector resistance. And here you go. And the answer is collector resistance. Is the collector resistance is constant all the time. So the collector current is not changed significantly by the collector resistance in the active region. If the base resistor of an NPN transistor is open, what is the collector current? 0 milliamps, 1 milliamps, 2 milliamps cannot be predicted. And here you go. And the answer is 0 milliamps. If the base resistance is open, then there is no path for the current to flow from the source to the base of the transistor, and hence the base current is 0 amps. That is all for this video. Thank you.